Bismillahirrahmanirrahim. Assalamu alaikum and welcome to this session. In today's session, we are going to talk about how can we mathematically analyze elementary queues. So we are going to model these elementary queues as birth-death Markov processes, and earlier in this course we have talked a little about birth-death Markov processes. Today we are going to extend that theory and we are going to see how that applies to the study of queuing systems. And secondly, in the later part of this session, I'm going to talk of perhaps the most important law there is in analytical modeling of computer networks. This law is known as the Little's law, which is a very important result that applies very generally, and it can be used to relate two very important performance metrics of any queuing system. And because of its wide application, it is very useful, and we would be using this extensively in the later part of this course. So these are the two agenda items for today's session. I will start by talking about queues as a birth-death Markov process. So if you recall our discussion on what a birth-death Markov process is, a Markov process is a process in which the next state you're going to move to is only a function of your current state. It does not depend on your history or the trajectory through different states into the current state. All that matters is that what state you are currently in. This is very useful because it allows us to forget all history and it leads to very simple analysis. We have seen earlier that a Poisson process is an example of a Markov process. So we are going to talk about that, but now let's talk about the birth-death Markov process. It is useful for modeling a queue because it represents a system in which transitions can be made from one state to the neighboring states. So you can move to the next higher state or the next lower state if you are not at the base state of having state level is equal to 0. In that case, you cannot go to the lower state. But in all other cases, you can make transitions to the adjoining states. And the important thing is that we cannot make any other transitions. The probability of making transition to any other state except your neighboring state is 0. So the analysis of this then becomes very easy. And I refer you to our earlier sessions where we developed the preliminaries of stochastic processes and our discussion on birth-death Markov process, but I'm going to still reiterate the major results. So having talked of a birth-death Markov process, we can talk of a special case of a birth-death Markov process, which is the Poisson process, which is very, very useful for our study of queuing theory, because practically all of elementary queuing theory assumes that the arrival process is Poisson. If our arrival process is something other than Poisson, we can in general state a few things about the system. In other words, according to the Kendall's notation, the first character always has to be M for us to say something useful about the queue. It may be an MM1 queue or an MG1 queue, but still if the first character is a G, we can say very little. So in a Poisson process, what is the defining feature of a Poisson process? It is a birth-death process in which you can make the transition to the next state. But the important observation that we can make here is that this is just a pure birth process in which you have no deaths. So if you observe the state transition rate diagram, you see that the rate of going from state 0 to 1 is lambda. The rate of moving from 1 to 2 is again lambda. And irrespective of which state we are in, the outgoing rate or the rate of going to the next higher state is always going to be lambda. And this is the hallmark of a Poisson process. So this can also be represented as a counting process. So this is also seen on the slide. you would see a staircase-like motion that always move upwards. And the inter-arrival time in a Poisson process is modeled by an exponential random variable. So all the successive inter-arrival times can be thought of as having been taken from an exponential distribution of a constant rate. So in summary, a Poisson process is a counting process. It's a pure birth process in which there are no deaths. So you will only keep on going upwards and upwards, and it has constant, independent, and stationary increments. So this thing is another important point, that the inter-arrival time is IID, which means it is independent and identically distributed from the exponential distribution. So now we can actually ponder on this and see if a Poisson process is actually a good model for a real life process. So in cases where the arrivals are coming from an infinite population, a Poisson process can be a good model, because if you have an infinite population, irrespective of how many customers have already arrived, the rate of new customers coming in can be imagined to be, the same. But in the case of finite population, it is often the case that if sufficient customers have already arrived, the arrival rate of subsequent arrivals would decrease. So we have to first of all take this into account, that are we modeling our empirical process by a Poisson distribution in the right way or not. In many cases, if our population is an order of magnitude more than the mean value we're considering, it does not really make a difference. But in some cases, it might make a difference. Also, a Poisson distribution has, between successive arrivals, the inter-arrival time can be modeled as an IID, exponential random variable. If you recall, the coefficient of variation of an exponential random variable is 1, which basically tells us that there is some variation, but the variation is not very wild. So it's not the kind of wild randomness that we've studied in the earlier part of this course. It is mild randomness, because the standard deviation is just equal to the mean. So essentially all of the values would be close to the central value. In computer networks, it has been observed that the network traffic has a lot more variation because of its self-similar nature and because of its fractal nature. And therefore, it is problematic to model network traffic by Poisson processes, because a Poisson process does not truly capture the bursty nature and the self-similar nature of network traffic. However, for the sake of approximation, we can still use Poisson models, especially because in elementary queuing theory, we only have results for Poisson processes. It is very hard to characterize any other system which has a general arrival distribution. So we will take this with a grain of salt. We know that our assumption is wrong. The network traffic cannot be exactly modeled as a Poisson process, as repeated measurements have shown. And in fact, even approximate characterization of network traffic is also problematic. So we need to have this in our mind, and the results that we get from our analysis of the elementary queuing systems that we will study should only be taken as approximations and as ballpark estimates. Like, we should not, on the basis of the elementary queuing system models that we're going to study, say that a router should have exactly these number of buffers. But using Poisson arrival process and associated mathematical formalism for the elementary queuing system, we can say that, okay, if we assume Poisson arrivals, these are the results that we have, and we can provision according to that. And typically, when we do analysis based on Poisson arrivals, our results are better than they would be if we consider self-similar traffic. So accordingly, when we use the analysis of queuing systems, as we will study, we should multiply that by some safe amount, and then apply the new number as the provisioning measure that we'll be using in our actual computer network. Okay, now having talked of some drawbacks of Poisson process modeling for network traffic, now we come back to the mode of where we actually are going to use Poisson traffic to understand queuing systems. So for that, we are going to now cover some important properties of Poisson processes. The first important property is what is known as the superposition of Poisson processes. In summary, if you have multiple Poisson processes and you aggregate them, you still get a Poisson process at the output. Only that the output Poisson process will have a rate which is the sum of all the constituent Poisson processes. This can be seen on the screen now. You see that there are n number of Poisson processes that are being aggregated. And when we have the pool stream, the rate lambda of the pool stream would be equal to the summation of the rates of the individual Poisson streams that are being aggregated. This will be useful when we study queuing networks. So I will emphasize here now that initially, as we develop the queuing theory part of this course, we will only be talking of single queuing service systems in which customers go to a server or a group of server for service, and that's it. You do not have a network. But when we want to model computer networks, actually we have a network of queues. So we have to queue up for service at one point, and then the departure of this process are then connected to some other queue, and you can have a general network. So when we consider queuing networks, we would see that this property is very important, because we know by now that analysis with the assumption of Poisson arrival is very convenient. For other models, it is quite complex. So we want our arrival patterns to be always Poisson if at all possible. So this is a good result, that if we aggregate multiple Poisson streams, you get a single Poisson stream with an increased rate. This operation works in reverse as well, in which you can actually decompose a Poisson process into multiple Poisson streams of smaller rates. So you can imagine that you have a Poisson stream, and this is being probabilistically routed to different queues. So the probability of going to Q1 is P1. The probability of going to Q2 is P2, and so on till the Qn, where the probability of going to is Pn. And then it's just the reverse operation of what we've studied when we talked of superpositioning of Poisson process. If you have a Poisson process of rate lambda and it is being decomposed, the decomposition is actually dictated by the probability of going to particular destinations. So if the probability of going to a certain queue is P1, then the rate of that decomposition is lambda P1. So in effect, we see that this is just the reverse operation of the superpositioning, and the rate at the input and at the output is still the same. It's just that we have decomposed the incoming Poisson process into multiple Poisson streams at the output according to the probability that we've chosen. So this is again a useful property when we will study queuing networks. Okay, now we get back to the mode of mathematically analyzing birth-death processes. And I would encourage you to go and actually revise the lecture that we had on birth-death processes. And we are actually going to just state the results we have developed there, and we are going to move forward. So if we have a birth-death process, when is this birth-death process stable? In the sense that we don't want a system that goes to infinity. So we want a recurrent system in which, the states you would again visit the same states again and again. And this is how we want a queue to be. We don't want a queue to grow unbounded in size. We want that when a customer comes, we may buffer it for some time, but we don't want our queue to have customers in it at all times. Ideally, we would like to have idle times as well, because that is telling us that the queue is performing well. So if we consider a single Poisson process, is it stable or not? So this is easily answered by saying that a single Poisson process is unstable because it's only a birth process. It will keep on increasing and there is no mechanism for pushing it back to an empty state. So a Poisson process on its own is an unstable system, and every state is transient. You're in a state, the arrival would come, and then you would move to the next higher state. And because of that, we don't have any solution of this. We cannot determine steady state probabilities. So how can we make a birth-death process stable? So the answer to that in general is that on the bottom of the screen you see that a general representation of a birth-death process in which the arrival rates are represented by lambdas and the service rates are represented by mu's. So what you want is that, okay, we may allow the queue to increase to a certain size, but beyond that, we want the service to actually push the number of customers back. So a concise statement of this condition is that for a birth-death process to be stable, there must exist some state, that state is J naught, we express that state by J naught, beyond which mu J is greater than lambda J for all J greater than J naught. In other words, when you go beyond that state, all the service rates are more than the arrival rates. And because of that, there would be a tendency for you to have decrease in the state, the number of customers in the queue. So in that sense, the birth-death process becomes stable. Let me again state it. If we have a queue which keeps on growing in an unbounded manner, this is an unstable system. We want a stable system in which the growth in the queue should be bounded, and ideally, when it grows, thereafter it should also be serviced so that the queue then becomes of a very small size or preferably becomes idle again. So this is the stability condition of a birth-death process. We've also covered the equilibrium solution of a birth-death process. What is the meaning of an equilibrium solution? The meaning of this is that if we allow this queuing system to unfold over a long period of time, we would then have, if this system is ergodic, and this system would be ergodic if this is a stable system according to the condition that we've just mentioned, that beyond a certain state J naught, the service rates should be more than the arrival rates. If that is met, we can have a steady state probability distribution of being in different states. This actually tells us that what is the probability that we would have an idle system, the long run steady state probability. What is the probability that we would have exactly one customer in the system? And accordingly, we can actually have an entire probability distribution. We can find the probability for any arbitrary value of customers in the system. So the way we analyze this is by using balance equations, and we've also covered this in depth. So I'll be just stating the results that we've developed for the equilibrium solution of a birth-death process. We saw that P1, the probability of being in state 1, is equal to lambda naught divided by mu1 multiplied by P naught. And similarly, P2 was the product of lambda naught, lambda 1 divided by mu1, mu2 multiplied by P naught. And the result for Pj can also be seen on the screen now. The only thing that remains here is what is P naught? What is the probability of having the system idle? And that can be determined from the observation that the probability of being in any one of these states is obviously going to be 1. And if we use that, we can derive the expression that P naught multiplied by 1 plus summation of j from 1 to infinity, the product of I is equal to 0 to j minus 1, the ratio of lambda I divided by mu I plus 1. And this should be equal to 1. So we have all that we need. we can find out the value of P naught, and from that we can find out the values of Pj. We just need to know the lambda i's and the mu i's. So this was the journal birth death process. We'll make things more simple now, because in a journal birth death process, the rates were state specific. So because of that, you had lambda I, you had all those subscripts, you had mu i's. For different states, the service rates were in general different. But if we consider a very simple process, which we will now call as an MM1 queue, in which the arrival rates are constant, irrespective of the state, it's always going to be lambda. And the service rate is also constant, and it is also independent of the state. And because of that, it is always going to be mu. So we can drop all the subscripts that we had earlier, and we can have a more clear expression and a more simpler expression of the probability distribution of being in different states. Let me reiterate this. This may be obvious, but the probability of being in a state is actually the probability of having that number of customers in the queue. So P0 is the probability of having 0 customers in the queue. So for the simplified case of an MM1 queue, in which you have a Poisson arrival process, which is going to be constant, the arrival rate is going to be constant for all states, and you have a constant exponential server with constant service rate for all states equal to mu, we can actually get the results that are simpler than those that we had for the journal case. And this is because we can now make the simplification of dropping all the subscripts, and we can express the ratio of lambda over mu by rho, which is just the utilization factor. The utilization factor is the ratio of the arrival rate and the service rate. And as mentioned in the previous session, this should be less than 1 for the system to be stable. Now we can transform the equations that we had for a journal birth death process and use these simplifications of having constant arrival rates, constant service rates, and expressing lambda over mu as rho. We get the equations as shown on the screen now. Specifically, we calculate that P naught multiplied by 1 plus the summation of rho raised to j over j is equal to 1 till infinity is equal to 1, and the expression within the brackets is simply an infinite sum of rho raised to j. And if the expression of that is 1 over 1 minus rho, when we consider that rho is less than 1, and because we are placing that restriction for the series to converge, we get the value of P naught is equal to 1 minus rho. And this is a very fundamental result, and this is one thing that applies to all the queues. So this applies to general arrival patterns, and we can say that this applies to a GG1 queue in which you have infinite buffer space. So this is a very important result that applies very generally, and let us try to analyze what this means. So this result essentially tells us that the probability of having 0 customers in the queue is equal to 1 minus rho, where rho is the utilization. So if the utilization or the traffic intensity is less, imagine it to be 0.1, then the probability of being in state 0 or having 0 customers is equal to 0.9, which is actually a good indication of the performance of the queue. If on the other hand rho tends to 1, what will happen? So if rho tends to 1, P naught will tend to 0. In other words, you would always have a system that is busy, a clear indication of a system performing poorly. So we are analyzing the probability distribution of an MM1 queue. Up till now, we have derived the result of P naught, and we've seen that it is equal to 1 minus rho. We can calculate the expression for Pj in a simple manner now that the subscripts of lambdas and mu's can be dropped. we have a simple expression that Pj is equal to rho raised to j multiplied by P naught. P naught can be easily determined using the formula that we just derived, and in summary, the probability of being in state j, Pj, is equal to rho raised to j multiplied by 1 minus rho. So this essentially captures the entire probability distribution of the MM1Q. So we've already achieved a lot. We have obtained the probability distribution of the MM1Q, and on the basis of this, we can actually calculate the expected number of customers in the queue. How can we do that? We can do that by taking the expected value of this P naught and Pj. We can see that P naught is the probability of having 0 customers in the queue. So we would have 0 multiplied by P naught plus 1 multiplied by P1, and we take this summation, and from this we can calculate the expected value, and that is the steady state average of what we would expect to find, how many customers we would expect to find in the system. So this is a very important result that we would come back to later, and as explained, using this probability distribution, we can calculate the expected number of customers in the system. So this is kind of an ensemble average. So as mentioned earlier in this course, a stochastic process can have 2 kinds of averages. One average is the ensemble average, which has to deal with probability modeling and the expectation. The other thing that we can have is that we can observe a single sample path of a stochastic process, or a single realization of the stochastic process, and observe it long enough. And on the basis of that, we can also determine the time average of that stochastic process. So let us now deal with that. Up till now, we've seen how to calculate the expected value of mean queue length. Now we are going to see the time average mean queue length. And let me reiterate that for an ergodic stochastic process, both these averages are equal. In other words, if you observe a stochastic process that is ergodic for long enough and you determine the time average, it is going to be the same as the ensemble average. So now let us see how we can calculate the time average of the mean queue length, or the time average queue length. So for that, we have a graph in which we are plotting the instantaneous queue length against time. So we observe that the system started in an idle manner, and then you had one arrival. So the number of customers in the queue rose to 1, and then you had another arrival. The number of customers in the queue became 2, and after some time you had a departure. So in a sense, this instantaneous queue length is capturing what is happening in the queue. And if we observe this long enough, we can calculate the time average from this. How can we do that? We can do that by first of all determining the area under the curve. And when we can determine that, we actually distribute it over the entire time, and on the basis of that, we would calculate the mean value or the time average value of the mean number of customers that you would expect in the queue. That can be seen on the slide now. You see that the entire area under the curve has been distributed in a fashion so that we can determine the expected value of n. In this case, this is a time average. This is calculated as 1 over t multiplied by the integral of the function nt multiplied by dt. The function n, which is a function of t, is expressed in the top portion of this slide. So from this, we can calculate the time average, and the good thing about a stochastic process that is ergodic is that this time average would be the same as the ensemble average. So now look back at this result and we can understand the importance of analytical modeling. So if we were to use a simulation as we have used in this example, or observation of a real system, we would have to observe the system over a very, very long time. But we can instead calculate the steady state value, or what we call the ensemble average, by just using mathematical formulas, and we don't have to actually run long simulations. And that is the benefit of analytical modeling. And that is why we prefer analytical modeling over simulation wherever it is applicable. Many real systems are too complex to be captured exactly by an analytical model, but when we are dealing with simple systems, it is always preferable to use analytical models over simulation models and over experiments. And obviously, it helps to actually do two of these three things to actually calibrate your results. You can calibrate your experimental data with what you expect from the analytical model, because we do not know if our approximations are right. We do not know if our experiments are right. But if we have two things that are agreeing, that gives us more confidence. So one thing that is still relevant to the time average of the queue length is that this is a relatively hard task. We have to observe this, and then we have to take the area under the curve, we have to distribute it over all the time. A simplification that we can adopt is that we can exploit a feature of Poisson processes, which is known as the pasta principle, which is that Poisson arrivals see time averages. To illustrate this, let us see the same example again. Instead of now calculating the time average as, first of all, taking the area under the curve and then dividing it by the entire time, we can actually just inspect the number of customers in the queue just at the arrivals. And the arrivals would look at the customers in this system without considering themselves. So as an example, we see that in this system, there are these arrivals. So for all these arrivals, the number of customers that are observed in the system are written above the arrow. So one thing that you would note is that the arrivals themselves are not counted in the number of customers in the queue. The interesting aspect of pasta is that if the arrivals are Poisson, we can actually just take the average of all these numbers, and assuming that the process has run for a long time, this arithmetic average would actually converge to the steady state average, or would be the same as the time average if we were to do it in the manner explained earlier of taking the area under the curve and distributing it over all t. This is very useful, and we would have opportunity to return to it and inspect this in more detail. In summary, pasta principle is that the Poisson arrivals see the system as if it is in the equilibrium, and this is while it is not considering itself as part of the system. We can imagine the Poisson arrivals to be like a random observer. It comes at these random points, and it inspects the system, and if we take the average of this, we would have what exactly equal to the time average in the limiting case, where you have run the process for a very long time. While this may look obvious to you, or it may not look obvious, we can contrast this to a deterministic process. In a deterministic process that is stable, we explained this in an earlier session, the arrivals would always see an empty system. It would always be the first customer in the queue, and it would see that the system is always idle. However, the system is always busy in the example that we saw, and it depends on the relative values of the inter-arrival time and the service time, but we can clearly see that the pasta principle of arrivals seeing time averages is not present in deterministic arrivals. It is only specific to Poisson arrivals. We will now proceed to the second part of today's session. We're going to talk of Little's law. So Little's law is essentially the most general law that applies in model-based network performance evaluation. And it is named after J.D.C. Little, who actually gave a proof of this in 1951. Before this, it was a folk theorem which many people believed in without, having this theorem proved. But he gave the first formal proof of this. And this law is very useful because it relates two very important performance metrics. And it is also useful because it applies very generally. It applies to any black box in which the number of arrivals and the number of departures are the same. In other words, no jobs are being lost. If that condition is met, then Little's law requires very few other assumptions. In particular, it does not require any assumptions about the arrival distribution or the service distribution or even the queuing discipline. It does not matter if your queue is using first come, first served, or it is using last come, first served, or it is using any other variant. Similarly, it does not matter if the arrival process is Poisson or it is from a general distribution. The rule still applies. To understand Little's law in depth, first of all, let me introduce some performance metrics that we use to characterize queuing systems. So the first performance metric that I want to talk about is the backlog in a queue, which is essentially how many customers are still present in the queue. We would call this the mean number of customers. And we can express the same thing in many different ways because we can analyze a system from very different viewpoints. We can analyze the system by expressing the number of customers that are waiting in a queue. So when I say waiting in a queue, that excludes the number of customers that are actually obtaining service. I can also talk of the number of customers obtaining service. This may be more than one if you have multiple servers. Also, we can talk of the number of customers in the entire system. When I talk of the number of customers in the entire system, this actually includes both the customers in service and also those that are waiting for service. The expression or the notation used for these terms is that we express the number of customers in queue by capital NQ, and this is a random variable, so this would change. So this thing is a random variable and it is a function of time. Also, the number of customers obtaining service is expressed by NS, and the number of customers in system is expressed as N. And this capital N is equal to capital N subscript Q plus capital N subscript S, which is essentially that the number of customers in system is the sum of the number of customers that are obtaining service and those that are in service. The other important performance metric, which is equally important, is that how much delay do these customers face on average. So if we consider an average customer that comes to your queuing system, what is the delay that he would face? So if we want to express this, we can talk of the delay, the average delay waiting in queue. We can also talk of the average delay to obtain service. This is also known as the response time, and this includes the waiting time plus the service time. And we can also talk of the service time as the delay that is involved in taking service. The exact precise metric that we would use depends on the kind of queuing system that we are interested in. If we have a system, for example, we are waiting in a queue in Disneyland, then we are interested in the time it takes us to get to obtaining service. In other cases, for example, when a packet has to be routed onto a link, then we may be interested in the entire response time, and there is nothing special about the time spent waiting in the queue. We are more interested in the response time. So all these measures are important, and I must emphasize that all of these measures are also random variables. And because of that, we would be calculating their expectations. And we want to have a system or some relation, when we can calculate a few of these, maybe by measurement, and then we can calculate the rest of them using some mathematical formula. And that is precisely what Little's law does. It relates these two important performance metrics. So Little's law has actually shown that the mean number of customers in a queue is directly proportional to the average waiting time of customers. And this can be understood intuitively. So for example, if it's a rainy day, then the mean number of cars on a road would increase. And because of that, the average waiting time that a user experiences using a car on these roads would also increase. So both of these two things intuitively are linked together, but Little's law actually tells us that they are proportional, but Little's law also provides us with the constant of proportionality. Let me now state the law. Little's law essentially states that the time average of the queue length is equal to the product of the arrival rate and the customer average response time. In other words, we've seen that N and R are proportional, and because these are random variables, we take expectations of these. We say that expected value of N is directly proportional to the expected value of R. N here is the mean number of customers in the queue, and R here is the average response time. And they are related in the sense that E of N, which is the expected value of N, is equal to lambda multiplied by expected value of R. So this is a very simple result on its face, but this is also considered a very deep result because of its wide application. We see in the little graph at the bottom of the slide that lambda represents the arrival rate, and the expected value of N is what we expect to see, the number of customers that we expect to see in the whole system on average. And the entire response time is actually the time it takes to get into the system and get out of the system. So if you want a simple way of remembering this, you can actually use the mnemonic of breaking down law as length is equal to arrival rate into waiting time. And in fact, if you observe queuing theory literature, you would see that in fact this is another representation of Little's law. It is often represented as L is equal to lambda W. And one thing that you would see if you read queuing theory literature is that there is a lot of notation. And unfortunately, many of these notations do not match. So because of that, in fact, even the notation that I'm using is a little different from the notation in your textbook, the Rajjan's book. But if you are exposed to more notation, as long as it is self-consistent, you would know that what different things mean, and hopefully you would find the notation self-consistent. Okay, if we want to understand Little's law intuitively, we can actually understand this and even prove this in a graphical manner. So let me now show you the stochastic arrivals and departures into a queue. So we see a graph here. On the x-axis we have time, and on the y-axis we have which customer is in the system. This is not the same as the number of customers in system. This actually tells us which customer is currently in the system. So you can see the arrival process, and we express this as a function of t, and we write this as a of t. And we also have a departure process, and this is expressed as d of t. So we're interested in finding the rate lambda, which is actually the arrival rate, and it's actually the reciprocal of the expected value of inter-arrival time. The inter-arrival time is an IID, exponential random variable, represented as tau. So lambda is equal to 1 over expected value of tau, and lambda itself is not a random variable. It's just a mean average value. So we have the first thing that we need for Little's law, the arrival rate, and now we will see how to interpret the number of customers in system. In other words, we want to determine the number of customers in a system for particular instances in time. We want to determine n of t. To do that, we would see that at this instant t is equal to t naught. Up till that time, 3 arrivals have occurred and also 1 departure has occurred. And because we know that no job is lost inside the system, there must be 2 customers in the system at time t naught. Similarly, you can determine that at t is equal to t1, the number of customers in the system is equal to 1. Since n of t is a random variable, we are interested in the long run steady state time average of nt, which for the case of a long run would be equal to the expected value of n. So how do we go about determining that? We can do that by breaking down the total area into vertical columns in this way, and then we arrange it with the x-axis. So this gives us the function n of t, and this is actually telling us that for different times how many customers are in the system. We can take the average of this by calculating the total area and then dividing it over the entire time. We have done that in the graph here, and we represent the height of this rectangle as n, and this is the average number of customers in the queue. If you are going to consider this graph for a long time, this will converge to the expected value of n. We can also consider another average, and for that we will have to break down the total area into response times. And for that, let us go back and consider what response time is. So on the slide now, you can see that response time of customer 1 is shown, and similarly for the other customers. It is the time between the arrival of customer and the departure of that customer. So if we want to determine the average customer response time, we can actually take this graph and break it down in a similar way as we've done for the number of customers in the queue, and we align it with the y-axis. Now the vertical axis captures the response time for each customer that arrived before t. So what is the average response time? We can do that by dividing the entire area over the y-axis between the region of 0 to the arrivals till time t, and we get this box. So in a sense, we've broken down the total area in 2 different ways. The area did not change, and we've broken down the area in 2 different ways, which involves averages. One was the average number of customers in the queue, the other was the average response time. Now we're in a position to relate both of these 2 things. So we see that n into t, which is the area of the red graph at the bottom of the slide, is equal to a of t into r, which is the area of the yellow rectangle. A of t is simply the rate multiplied by total time, and because of that we have the equation n into t is equal to lambda t r. Now using simple manipulation, we calculate n is equal to lambda r, which is our Little's law, and in a relation between expected values we can express this as the expected value of n is equal to lambda multiplied by expected value of r. We would see that we can consider Little's law in both the setting of stochastic processes and also in the context of sample paths. And we will study that when we do something known as operational analysis later on in this course. So, as mentioned earlier, one of the major points of Little's law is that it can be applied both at the level of the system and also at the level of a subsystem. We can apply this law at the level of the queue itself. We can exclude the number of customers in service and also the time of service. And the relationships for that is shown on the slide. I'll wrap up this discussion by giving you an example of Little's law. Assume that you receive 50 emails every day and that you archive your messages after responding to your email. The number of unresponded emails in your inbox varies between 100 and 200, but its average value is 150. Now the question is, how long does it take on average to answer your emails. So this is a perfect question for applying Little's law. We have two variables given and we need to calculate the third one. We know that the average number of emails in your system is 150, so n is equal to 150. The average arrival rate is 50 emails per day. So we can calculate the average time it takes to answer your emails by taking the ratio of n and lambda, and this comes out to be 3 days. Okay, now let me wrap up this session by telling you the salient points that we've discussed today. We've seen that queues can be characterized by birth-death processes, and even more simply, we can express queues by birth-death processes with constant arrival rates and constant service rates. We'll be using this to develop particular queues in coming sessions, and we've also seen that Little's law is a remarkably general law that relates to primary queuing performance measures, the mean number of customers and the mean response time. With this, I come to the end of today's session. I'll see you next time, inshallah. Assalamu alaikum.